So let's go back to the control block, the closed loop transfer function block diagrams that we've been analyzing. And we'd expect something that looks a bit like this. And figuring out how we design a good controller, a GC block that is able to appropriately handle disturbances and perturbations in a process is challenging. And so we use things referred to as PID controllers, and PID controllers can have up to 3 tuning parameters that we need to adjust for, and determining what those 3 tuning parameters are is where things are tricky. And direct synthesis along with the internal model control are 2 ways that process control engineers in practice are able to determine what parameters to go with. And the nice thing about direct synthesis as well as IMC is that we only will have to tune 1 parameter, lambda, in all of our models to obtain the other tuning parameters in the PI or PID control that we end up getting. And so to start off with, if we take this classic closed loop transfer function and we analyze the response, in other words, how does an output, which is y, respond to an input change, our set point, for instance, we would get something like this. We would have GC times GP divided by 1 plus GC GP. And this denominator is the characteristic equation of our closed loop transfer function, which we will see in any response in our system involving y as an output. And so what we do in direct synthesis is we will directly put in what response we want our system to have. And by that I mean we will let this term here be equivalent to a term called GCL. And GCL is the desired response. And so what we're going to do now is take a step back and ask ourselves as control engineers, what kind of response do we want our system to have? And in practice, the best response we can hope for is first order dynamics. And so ideally we would want GCL to be equivalent to 1 divided by lambda s plus 1. So this is a first order response because the degree of our denominator is 1. S is only raised to the first power. And because our gain in this case is 1, means that we have offset free tracking. And because the denominator had degree 1, it means that we have no oscillations. Because we want to minimize oscillations in practice because they can have detrimental effects on our process. And so now that we've done that, there are some multiple cases, but as an introduction, we will consider minimum phase dynamics. Minimum phase dynamics, which implies that we have no right-hand plane zeros. And so what right-hand plane means is it refers to the real part of the zeros, which are the roots of the numerator in our process block. And so we're going to be assuming in this example that GP, our process, which is a physical characteristic of our system that we have no control over, has no numerator dynamics, and we don't have to take that into account, and it is also a first order system. And so now that we've done that, I'll go through how we can determine what our tuning parameters for our PI or PID controller should be on this first order process. And so we're going to be given some generic first order process, GP, which will be equivalent to some process gain, KP, divided by tau PS plus 1. This is a first order system. no numerator dynamics, and that's it. And so what we do in direct synthesis here is we will solve for GC as a function of the closed loop response that we want. And what we'll find after some algebra substitutions is that GC is equal to GCL divided by GP times 1 minus GCL. And I encourage you to prove this and do the algebra, but for the sake of continuing, we will say this. And so now that we know what GC is, and we know what GCL should be for this minimum phase system that we have, we will plug and chug. And so what we'll find is that GC is equivalent to 1 divided by lambda s plus 1 divided by GP, which we've already established was Kp divided by tau ps plus 1, quantity times 1 minus 1 over lambda s plus 1. And so you'll note here how this is really equal to lambda s over lambda s plus 1. And continuing to simplify down this problem, what we would find is that GC is equal to 1 over lambda s plus 1 times, and then the inverse, so tau ps plus 1 divided by Kp times lambda s plus 1 over lambda s. We'll note here how these two terms cancel out, and we're left with GC is equal to tau ps plus 1 divided by Kp times lambda s. So that's a good point to be able to get to. And the next thing we do is recognize how the standard PI controller control function GC has the form of Kc times tau is plus 1 divided by tau is. So this form right here is the P part. This part is the I part, the integral part of the PI controller. We can rearrange GC into this form. And so when we do that, we simply just multiply the top and the bottom by tau P over tau P. What we find is that this GC is equivalent to tau P divided by Kp times lambda times tau ps plus 1 divided by tau ps. And the key takeaway from this is that we have now defined Kc, and we also will recognize that tau p should be equal to tau I. And so that's a big takeaway from this direct synthesis model, is that the physical time constant of our process, that is a physical property, we should let that time constant be equivalent to our integral time constant, and that takes away a tuning parameter, tau I, that we have to worry about in our PI controller. And then also we know that our gain, our controller gain Kc, should be equivalent to tau p over Kp times lambda. The only tuning parameter we have to care about now as a process control engineer is what to make lambda. And so lambda is a trade-off between performance and robustness. And so what I mean by that is if we want a controller that will very quickly get our system back to the set point value after it's been perturbed, we're going to want to opt for having a very aggressive controller. And so what we'll note here is that as we decrease lambda, we will have an increase in our controller gain because it's inversely proportional, as we can see, and therefore our system will be more aggressive. And more aggressive can get us better performance. We're going to return to a new set point more quickly. However, when we decrease lambda, we do so at the cost of robustness. Because our models aren't perfect, there can be inaccuracies present, and if we make our lambda too small, it can, at a certain point, our system will become unstable because it can't handle anything other than the exact perfect model, which, as we all know, isn't perfect. So that is the major trade-off, and this is the main takeaway that we get from the direct synthesis. And so we do see the same results that we get if we did the IMC method, but the direct synthesis method is also another way that you must know how to use as a process control engineer in practice. And so this concludes the direct synthesis method for PID design with a first order process as well as an introduction. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.